Welcome. This is a review of derivatives of trig functions. And so this is the second time I've done this. My video is a little long. I'm going to try to do it a little faster, which means I'm going to talk a little faster. All right, so all of these, some of these will involve a chain rule. Some will involve a product rule or a quotient rule, but not our first one. We have just a constant multiple, and this just couldn't be any easier because the derivative of 2 sine x is 2 cos x. That was an easy one. 41 seconds. All right, let's look at the next one. Now this one would involve a chain rule because we don't just have an x, we have a 2x. Okay, so our outside function is cosine, that's a c, blop. And the inside function is 2x. Derivative of the outside function is negative sine blop. And the derivative of the 2x, the blop, is just 2. So the blop is going to be just what the blop was before. Okay? So our derivative, we're just going to take then the two derivatives, the outside and the inside, and I'm going to put the 2 first. We have a negative, actually, I'll write it this way, so, and then I'll simplify it, just to make sure everyone understands. Negative sine 2x times 2, which we can rewrite as negative 2 sine 2x. The next one combines a little of both here. We have a constant multiple, and we have a chain rule. So our outside function is 2 sine blop, and the inside function is the 2x. The derivative of the outside would be 2 cosine blop. And the derivative of the 2x is, of course, 2. So our derivative here is the derivative of the outside function, the 2 cosine blop, which is the 2x, times the derivative of the inside, which was the 2. And now we can just multiply the two 2's there together and call it 4 cosine 2x. And that's our derivative. So easy cheesy lemon peasy on the first set here. This next one, and it's not harder, I don't think. We can rewrite this as y equals tangent x all squared to help you think about the derivative, and that this would be a chain rule. The outside function is blop squared. The inside function is the tangent x. Derivative of blop squared is just 2 blop. Derivative of tangent x is secant squared x. And the derivative of the whole thing is going to be 2 blop. What goes in the blop is the tangent x. So 2 tangent x secant squared x. And we're done. All right? And now we have very similar problem here, except this will involve 2 chains instead of just 1. So we have our outside, I'm going to rewrite that so we can think of this as cotangent 2x all squared, right? And so our outside function is 2 blop, and the inside function, the more inside function, is cotangent blop, and the most inner function here is 2x. So the derivative of 2 blop is, oops, I already took the derivative, sorry, it's blop squared. And the derivative is 2 blop. Got carried away. So sorry, the function is blop squared. The derivative is 2 blop. Okay. Ooh, those are the worst looking parentheses I've ever seen. And the derivative of cotangent blop, it's a lot like the derivative of tangent, except it's negative, and it's cosecant. So it's cosecant squared blop, and then the derivative of 2x is still 2. Of course, what goes in the blop? Of course, we know that this goes in the first blop. In the second blop would be the 2x. Okay, so what's in the blop is just what it was before. It doesn't change at all. Oops, that's supposed to be a 2x there. And so our final derivative, dy dx, is the outside derivative 2 cotangent 2x times, moving inward, negative cosecant squared 2x and the 2. So you see, if you write all of your functions just working your way out, you write your f of x, your g of x, your h of x, hey, maybe you'll have an I of x, and just take the derivatives of those, your final derivative is just the products of all of those derivatives on your chain rule. So I think that's an easier way to think of it. So let's combine all of these 2's, well, 2 of these 2's, and the negative there, and call that a negative 4. And then cotangent 2x cosecant squared 2x is our derivative. Hey, that wasn't that bad, was it? I have 15 here. Let's see if I can keep this pace. Y equals secant square root of x. This would be a chain rule. I can rewrite this. I am going to rewrite this as y equals secant x to the 1/2. Right, so our outside function is secant blop, and the inside function is x to the 1/2. So because it's not just an x, this would be a chain rule. And so the derivative of secant blop is secant blop tangent blop. And the derivative of x to the 1/2 is just the power rule. 1/2 x, subtract 1 from your exponent, negative 1/2. And I'm going to simplify that and make that 1 over the square root of x. That looks a little nicer. And so our derivative here, dy dx, is derivative of the outside function, secant, and we're going to fill in the square root of x, tangent square root of x, times, parentheses here, 1 over the square root of x, and let's just make that one fraction here. So dy dx is secant square root of x, tangent square root of x, all over the square root of x. Definitely the derivative is a little more involved than the function was, huh? But this is the equation that would describe how we would find our slope, and it describes our instantaneous rate of change. Would be our derivative, of course. So kind of a complicated derivative there. You got 7, 8, 9 here. Y equals square root of tangent x, slightly bit different than the problem we had just done. We can think of this as tangent x all to the 1/2 power. So you do have a chain rule here. The outside function is blop to the 1/2, and the inside function is tangent x. So f prime of x would be 1/2 blop to the negative 1/2. Derivative of tangent x is secant squared x, and the derivative of our whole function here is going to be, I'm going to simplify that a little bit here. So we have 1/2 blop to the negative 1/2. I'm going to just rewrite that real quick. Of course they're attached. I'll erase the g of x and we'll just move it over. All right, so I'm going to just make this f prime of x a little simpler and call that square. So the only thing that's going to be left in the numerator is the 1. And the 2 and I've got now blop to the 1/2. So that looks a little nicer. G of x was the tangent x, and its derivative is secant squared x. So dy dx is 1/2, and in the parentheses should go tangent. I'm going to write that as square root instead of 1/2. So 1/2 times the square root of tangent x, and then times secant squared x, and let's combine that and make that one fraction. Dy dx is secant squared x 2/2 square root of tangent x. And there it is. Okay. All right, the next one, only a little bit different. Instead of it's cotangent instead of tangent, but it's 2x instead of x. So that gives us one more part to our chain here. So I'm going to rewrite this as y equals cotangent 2x to the 1/2 power. Our outside function is the blop to the 1/2. Moving inside, we have cotangent blop, and then the derivative of the blop 2x. All right, so derivative of the outside is going to be 1/2 blop to the negative 1/2. I'll just simplify it when we do the final derivative. Derivative of cotangent blop is going to be negative cosecant squared. I wrote my letters backwards. Negative state. Cosecant squared blop. And then the derivative of the 2x is still 2. You should have that memorized by now. So our final derivative is going to be derivative of the outside portion. So I have, I'm going to try and simplify this a little bit as we go here. So since it's 1/2 blop to the negative 1/2, let's just put the 2 in the denominator here. And let's make that in the denominator, and that was the cotangent 2x. That's what goes in our blop right here, cotangent 2x. Right? Times the, moving in a little bit, we've got the negative cosecant squared. Right, so I'll just put that like that. And then I'll simplify it in my next step. So times the negative cosecant squared blop, and of course the blop is 2x. And then times a 2. Well, those 2's are going to cancel, aren't they? So those are going to be gone. Well, maybe this one's going to be gone. Who knows? And so we'll have dy dx is, we have a negative cosecant squared 2x in the numerator there. And in the denominator, we have the square root of cotangent 2x, and there is our derivative. Okay. So yeah, they look a little bit alike, don't they? Except for a sign, but because it was a 2x instead of an x, a little bit different coefficients there. Well, sometimes a very easy function, you think it can't be that easy, and you try to make it really complicated problem out of it, and this just couldn't be any easier than this. This is just sum and difference. So the derivative of sine x plus cosine x, derivative of sine x is cosine x, and the derivative of cosine x is negative sine x, and that's all there is to that problem. So I want to throw an easy one in there just because sometimes you think something might need to be complicated and it's really not, and that was a really easy derivative. All right, I got 6 more for you. Right. These look an awful lot alike, but the derivatives are a little bit different. All of them will involve a chain rule. Right. So the first one here, our outside function is 6 cosine blop, and the inside function is the x squared. Derivative of the outside function is going to be negative, right? because it's going to be negative 6 sine blop. And the derivative of the x squared is 2x. So our final derivative of the outside times the derivative of the inside. So we have a negative 6 sine, and blop should be an x squared now, times the 2x. And let's just multiply the negative 6 and the 2x together and call that negative 12x sine x squared. And there we go. All right, so now the other one's not an x squared. It's y equals 6. The 6 is not raised to a power. Cosine x all squared. Okay, so now we have a chain rule, a slightly different chain rule. Okay. All right, so our outside function is 6 blop squared, and our inside function is going to be the cosine x. Derivative of the outside, we'll just multiply the 6 and the 2 together and get 12 blop. And the derivative of cosine x is negative sine x. Okay. So our derivative, dy dx, is going to be the derivative of the outside, 12, and the blop is cosine squared x, times the derivative of the cosine x, which is going to be negative sine x. And don't leave that negative hanging over there. Instead, make this negative 12 cosine squared x sine x. Or if you want, you can put the sine x first. Okay? It doesn't matter. Either way, it's okay. Okay? So if you like it the other way, sometimes I like to put the lower exponent first. We can make it negative 12 sine x cosine squared x. Same thing either way, though. All right, so now we have both of those two things combined together. This would be a chain. I'm going to rewrite this as 6 cosine x squared all squared. All right, so our outside function is 6 blop squared. Moving inside, we have cosine blop. And one more chain, one more function there. We have an x squared. It's not just an x, and the other one was an x. So we didn't have to take the derivative of an x, it's just one. But we do have to take the derivative of the x squared and include that. So the derivative of 6 blop squared is going to be 6 times 2, or 12 blop. The derivative of cosine blop is negative sine blop. And the derivative of the x squared is 2x. So our final derivative, dy dx, is, I'll write the first one first. 12, and it was cosine x squared is inside that, in that blop there. And then inside the next blop, it's negative sine x squared. And then our final would be 2x. Okay, so let's clean this up a bit. And I'll put the final answer in red, because it's our last step. So we should multiply the 12, the negative 1, and the 2x. And that gives us negative 24x. And it doesn't matter who's first. Cosine x squared sine x squared. And there's our derivative. So this goes right there. That's the blop for that portion. Oops. And it's the same blop. Just the x squared goes here. Okay. And now we're all done. So even though they look a lot alike, you can see their derivatives are very different, because we have in the first one only x is squared. In the second one, you've got cosine and x being squared, and in the third one, you've got x squared twice, and you've got cosine squared. Okay, so a little different. I have 3 more. I am going a little faster than I did the first time I did this video. All right, so we do have a chain rule here. I am going to rewrite that as y equals secant 2x plus 1 all cubed. So outside function, we'll have 3 here, will be blop cubed. Moving inside, okay, so you just move it inside, you have secant blop, and one more, the blop, the 2x plus 1. So the derivative of blop cubed is 3 blop squared. Derivative of secant blop is secant blop tangent blop. And the derivative of 2x plus 1 is 2x. Okay? And of course, oops, all of this goes here. But we're working in, and so just this portion goes here. All right, so let's get our final derivative here by just multiplying all of our derivatives for each of our functions here. So dy dx is going to be 3 secant 2x plus 1, and that is squared. And actually, I'm going to put the square right there. And then times secant 2x plus 1 tangent 2x plus 1 and times a 2x. So let's combine the 3 and the 2x. I think that's it. And for the coefficients. And we can combine these guys as well. Square times one more is a cube. So our final answer is 6x secant cubed 2x plus 1 tangent 2x plus 1. And there we go. So definitely the derivative is a little more involved than the original function is, but if you want to know the slope of your tangent line, you'll need to find the derivative. I have 2 more. So we have 4 secant 3x tangent 3x. This is a product rule, and it's got quite a bit to this. Just as a reminder on the product rule, that it's your derivative, when you have a product, is going to be the first times the derivative of the second plus the second times the derivative of the first. Okay? So our first, we'll put the 4, of course, we'll call it 4 secant 3x. We could, take the 4 out and multiply it at the end there, but I'll just put it right there. And then the v is, give myself some space here, is the tangent 3x. So we want to take the derivatives of those, and I know that's going to take us a little bit of space because both of them are chains. Our du is, well, first of all, let's talk about the outside portion. The outside portion is the 4 secant blop, and then our inside portion is the 3x. All right, so let's take care of this one. The derivative of 4 secant blop is going to be 4 secant blop, tangent blop, and the derivative of the blop, the 3x, is 3. All right, so let's do the same thing. So, before we do that, let's write down our derivative. So the derivative of the du here, the derivative of u, the 4 secant 3x, is going to be, we're going to multiply the 4 secant blop, tangent blop, or 4 secant 3x, tangent 3x, times the 3. So we've got 3, 4 secant 3x, tangent 3x, which makes this 12 secant 3x tangent 3x. All right, so now same thing, new function. So the outside, oops, oh, no, right in black. The outside is the tangent blop, and the inside is the 3x. The derivative of tangent blop is secant squared blop, and the derivative of 3x is still 3. So that makes our dv, I'll put it over here, I guess. Our dv is going to be 3 times secant squared blop, or 3x. So 3 secant, come on, squared 3x. Okay. So now we have all of our players. Purple here. We have the u, we have the du, we have the v, and the dv. And let's just plug that in to get our derivative here. All right, so dy dx is the u for secant 3x times dv, which is 3 secant squared 3x, plus, because I don't have enough space going across, the v, which is tangent 3x, times the du, which takes up quite a bit of space. And we'll just squeeze them right here. So 12 secant 3x tangent 3x. And let's clean this up, because we certainly can. So dy dx, hope you don't mind kind of following all these steps down here. And they literally look like steps. So we could multiply the 4 and the 3 and call that 12. Okay. We could also multiply the secant 3x by secant squared 3x, and it would be just like multiplying x times x squared in this case, since they both have a 3x. So that would be secant 3x cubed. And then we have the plus. We've got a 12 here, so let's put the 12 in front. And then we have tangent 3x and a tangent 3x. Let's call that tangent 3x squared. And then we have the secant 3x. So secant 3x tangent squared 3x. I don't think there's anything else we can do, except maybe scoochie everybody over. Let's take a look. Nope, that's it, because these aren't like terms anymore. So here's our final derivative. 12 secant 3x cubed and 12 secant 3x tangent 3x squared. Okay? So that's our derivative. This was a little bit more involved because we had a product and a chain. Last one will involve a quotient, and I don't think it's that bad. So just remind us that the quotient rule is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. Okay? So the derivatives on this one are easier than the last one. So the u here, the numerator, is 1 plus sine x. The derivative of that is just cosine x, because the derivative of 1 is 0. And the denominator is cosine x. The derivative of that is negative sine x. All right, and let's just finish this off. So dy dx is, so our v cosine x times the derivative of the numerator, another cosine x, minus the numerator times the derivative of the denominator. So I've got another negative sign. I have another negative, so that's going to make it a plus. times the 1 plus sine x. I chose to write it like this. I never seem to give myself enough space. I should just know better. Because I want to make sure I simplify those negatives. All over cosine squared x. And now let's simplify this. So dy dx is cosine x times cosine x is cosine squared x. And then the two negatives become a plus. Let's distribute that, the negative there. Actually, they won't. Yeah, this will be, so I have a negative times a negative sine x times 1. That'll be sine x, right? And then I have a negative times a negative sine x times a positive sine x. That's going to be sine squared x, right? Excuse me, plus sine squared x. Oops, sorry about that. So I'm just distributing the two negatives and the sine x to both of those. So that's going to be cosine x squared x plus sine x plus sine squared x. There we go. All over cosine squared x. Okay. We could simplify this a little bit. So let's put the cosine squared x and the sine squared x together. And what do they make? Well, they make 1. It's just Pythagorean identity there. So let's just replace these guys with 1, which gives me my final answer. dy dx is 1 plus sine x all over cosine squared x. And look how much the derivative looks like the original. Difference just by a cosine x in the denominator. So I hope this has helped you with the derivatives of trig ratios. I wanted to be under 30 minutes, didn't quite make it, but pretty close. So you can take a look at this when you're solving your homework on the trig derivatives. See you in class.